Chemical kinetics is the study of the rate or speed at which chemical reactions occur. In biochemical reactions, the term reaction velocity is sometimes used. In the study of chemical kinetics, which we often refer to just as kinetics, we ask the following questions. How does the rate of a chemical reaction depend on the concentrations of the reactants? How does changing the temperature and/or adding a catalyst change the reaction rate? What is a useful way of thinking about how molecules react with one another? For example, do they have to actually collide with each other or just be near each other to react? Can we get some idea of whether or not a reaction occurs in steps? That is, can we construct what we would call a reaction mechanism that gives us a molecular level view, in other words, a series of elementary reaction steps. It'll give us a molecular level view of the path from reactants to products. If we can do this, this would give us some ideas about how to intervene to either speed up or slow down a chemical reaction. A generic representation of a chemical reaction is shown below. And in this generic representation, we have, as typical for chemical reactions, the reactants written on the left as A plus B with coefficients small a and small b, and products written on the right with coefficients small c and small d for the two products. In the middle, we've put something that's not typically put in a chemical equation, and that is a blue box that says reaction mechanism, series of elementary reaction steps. Well, the inside of this reaction mechanism box is for the most part not available for viewing, meaning many times we don't know exactly what's going on in this box. However, from studying the kinetics of the disappearance of the reactants A or B, or the appearance of products C and or D, we can make important inferences about what reaction steps or elementary reactions are occurring in this box. Why is this important? Because we often just write reactants, arrow, going to products, and we don't think about the steps that are necessary to get from reactants to products. And those steps are very important in figuring out how to either speed up or slow down a reaction as we would want to do. So this reaction mechanism box is kind of mysterious to us. And again, we can't see directly in this box and watch any series of elementary reaction steps occurring, but we can infer what might be going on in here from studying what we call the kinetics of the reaction, the disappearance of the reactants and or the appearance of the products. So let's begin our study of kinetics by simply examining how we express reaction rate. Now, generic reaction representations are usually shown without the reaction mechanism box. So we've rewritten our generic reaction here with that reaction mechanism box missing. Now let's write out an actual reaction. This is a reaction which is technically called the hydrolysis of butyl chloride, actually T-butyl chloride. Hydrolysis just means reaction with water. So what we're doing is we're reacting T-butyl chloride with water to form T-butyl alcohol and hydrochloric acid, HCl. We can take a 3D view of this reaction just to make it a little more interesting. You can see this T-butyl chloride is C4H9Cl, and it has the following shape. The carbons aren't all in one string. It actually has kind of a T shape, and the chloride is attached on this middle carbon. Of course, it reacts with water, which is a bent structure, and forms T-butyl alcohol. And in this case, we've substituted an OH group from the water for the chloride, and the chloride then reacts with the leftover hydrogen on water to form hydrochloric acid. Now let's suppose we monitored the rate of this reaction by measuring the molar concentration of T-butyl chloride at specific times as it reacts with water. So we're going to measure the concentration of this T-butyl chloride as the reaction proceeds. And as you can see, at time equals 0, we're starting with 0.1 molar T-butyl chloride. You want to note here that these square brackets around T-butyl chloride typically mean molar concentration. And it typically would mean that even if the unit molarity here were missing. So as the reaction proceeds, as you would expect, the T-butyl chloride starts disappearing with time because it's reacting with water and producing T-butyl alcohol. So as time progresses, the concentration of the reactant T-butyl chloride is going down with time. Let's make an Excel plot of this data. We'll do that on the next slide. So if we plot this data, as you can see, we have on the x-axis time in seconds. So we're plotting this column here for the x-axis. And on the y-axis, we have the molar concentration of T-butyl chloride at any of these marked times. And then we've connected the data points with a smooth curve. Now this plot is useful in that it illustrates how the reaction is slowing down as time progresses. For example, the concentration of T-butyl chloride decreases by about 0.02 molar from 0.1 to 0.08 in the first 100 seconds, but it takes from around 340 seconds to 460 seconds. It takes from about 460 seconds to about 800 seconds for the concentration to drop the same amount by 0.02. So the concentration of T-butyl chloride drops rapidly at the beginning, and then the drop in concentration starts slowing down as the reaction proceeds. Now it's possible to determine the average rate of the reaction. In this case, that would be equated to the average rate of the disappearance of T-butyl chloride over any defined time interval. And an expression for this can be written like this. And what we say is, this term right here we call the rate of disappearance of T-butyl chloride with time. You can see it's the change in the concentration of T-butyl chloride divided by the change in time. And since it's disappearing, we'll put a negative sign there. And the reason we do this will become clearer soon. The expression over here has the initial concentration of the T-butyl chloride at the initial time. And then we have the final concentration of T-butyl chloride at the final time of the time interval that we chose. Notice there's also a minus sign in front of this entire expression. So let's discuss these minus signs for just a minute. We will insist that a reaction rate, which is a change in quantity divided by a change in time, always has to be a positive number. We'll just insist on that. You cannot have a negative rate. Rate needs to be positive. So when a reactant is disappearing with time, and remember we're following the disappearance of one of the reactants, the T-butyl chloride, with time, the rate will come out negative unless we multiply by -1. So for example, on the right-hand side of this equation up here, since T-butyl chloride is disappearing with time, the final concentration of T-butyl chloride is going to be smaller than the initial concentration of T-butyl chloride over our time interval. So that will make this term negative. And so in order to get our rate positive, we're going to have to multiply by -1. Time can't be negative, so it's not the denominator's fault that this comes out negative. It's the numerator's fault. So let's look at the average rate over two different time intervals. So here's the table of data, and we'll look at the average rate in the time interval 0 to 100 seconds, and then the average rate in the time interval from 500 to 800 seconds. So how are we going to do this? Well, we're just going to calculate these rates, and we'll look at interval 1 first, from 0 to 100 seconds. The rate of disappearance of T-butyl chloride, as we said on the previous slide, is equal to this expression right here. We should just be able to fill in the numbers. We'll fill in the concentration of T-butyl chloride at 100 seconds minus the concentration of T-butyl chloride at the beginning at 0 seconds, divided by the time difference, 100 seconds minus 0 seconds. If we put in the numbers, we get 0.0820 molar minus 0.1 molar over 100 seconds. And that would come out negative, but remember we're multiplying by -1, so the number comes out positive, and we get a rate of disappearance of T-butyl chloride, which we'll consider to be the rate of the reaction, of 0.000180 molar per second. Let's look at the interval from 500 to 800. Again, we use the same general equation, and we're going to put in the concentration of T-butyl chloride at 800 seconds minus that at 500 seconds, divided by the difference in time, 800 minus 500. And again, we come out with a positive number because of this negative sign, and we get a rate of 0.0000560 molar per second. So we can see that the reaction rate is decreasing with time. The average rate of the reaction between 0 and 100 is this number, and the average rate between 500 and 800 is this number, and this means that the reaction is much faster at the beginning. In fact, it's about 3.2 times faster between 0 and 100 than it is between 500 and 800. The reaction is slowing down with time. Let's note some things here. The rate comes out positive, which we've said that's necessary. The units of rate here come out to molar per second. Molar per second. These are the most common units for reaction rate that you will see. However, keep in mind that the general definition of rate is a change in quantity divided by a change in time. In reality, the change in quantity could be other units, such as a change in pressure, and the time could be in units other than seconds. So for example, you could see a rate in units of atmospheres per minute. It's a change in some quantity per unit time. But molar per second will be the most common unit we'll see. The other thing is that both of these numbers seem quite small, and you might ask, is this a problem? And the answer is no, not really. It can actually be more of a problem if the reaction rates are too fast to monitor. We can monitor quite slow reaction rates because we can watch them over a reasonable time, When they become faster, we need instrumentation to do it, and sometimes they become so fast it's even difficult to do it with instrumentation. So no, these numbers are not a problem. So let's return to the plot of concentration versus time for this reaction to continue our discussion of average rate. What we actually accomplished on the previous slide was to find the slopes of each line connecting the 2 points on the graph for each time interval. So for example, I've drawn here a green line between points at time 0 and at time 100. And what we did to actually get the average rate was we found the slope of this line between 0 and 100, the slope of this green line. If you literally just calculated the slope, which of course is the change in y over the change in x, and you did it consistently in the right manner, you'll see here that if I take the concentration, the y value, 0.0820 molar, subtract the y value at time equals 0, and then take the x value, which would be 100, and subtract the x value here, which is 0, we get a slope of minus 0.000180 molar per second. That is the slope, but remember, the rate has to be positive. So if we found our rate by just finding the slope of this line, we get a negative slope, but we say, hey, rate has to be positive. So we're making that number positive. It's exactly the same calculation we did on the previous slide, only this time I'm just showing you that the number actually comes from the slope of the line connecting these 2 points. Same thing with the average rate that we found between 500 and 800. Again, the blue line connecting those 2 points has a negative slope. So you're going to come out with a negative slope. And since that really is the average rate between those 2 points, if we want to call it a rate rather than a slope, we just have to say, hey, we have to make it a positive number. Now we've seen how to determine the average rate of a reaction over a specified time period. Now, can we determine the instantaneous rate at any particular point in the reaction? And the answer, of course, is yes. But to do that, what we'd need to do is to shrink the interval that we are observing, the length of the green or blue line on the previous slide, until it becomes infinitesimally small right at the point of time we're interested in. That would actually mean doing calculus. We don't want to do calculus in this course. So what we're going to do is say that in practice, we can do this by finding the slope of the line that's tangent to the point on the graph where you wish to determine the instantaneous rate. We can illustrate this with an example, of course. So what we're going to do is determine the instantaneous rates for the hydrolysis of T-butyl chloride at both 100 and 800 seconds. So here's our graph, and I've pointed out T equals 100 seconds, so we're going to try to find the instantaneous rate right at 100 seconds. To do that, I've done the best I could to draw a red line that is tangent to the curve at 100, meaning technically it touches the curve right at 100. Now, of course, this is subject to some interpretation and error when you draw these. I've done the best I can here. And what we're going to do is now get the slope of this line that's tangent. So notice I'm picking 2 points on this line, and we're going to get the slope of this line. This is not the slope of the curve, it's the slope of the red line that's tangent to the curve at 100 seconds. If we go ahead and find that slope from these 2 points A and B, which I've pointed out here, and calculated the slope, we'd get a value of minus 0.00017 molar per second. And again, if we want to call that a rate, we'd have to make it positive, and we'd say the instantaneous rate at 100 seconds is 0.00017 molar per second. Now let's get the instantaneous rate at 800 seconds. Again, we do our best to draw a line that's tangent to the curve, touches the curve right at 800 seconds, and we're going to pick 2 points on that red line and find the slope of the line. And when I do that, I get a slope of minus 0.000040 molar per second. And if we say that's the instantaneous rate at 800 seconds, of course, we have to make it positive, 0.000040 molar per second. So you can see that the instantaneous rate at 100 is much higher than the instantaneous rate at 800 seconds, which is what we would expect at this point. Now, in future lectures, we will often refer to what's called the initial rate of a reaction. And technically speaking, the initial rate is the instantaneous rate at time equals 0. Well, we could extract the initial rate of the hydrolysis of t-butyl chloride by determining the slope of the line tangent to the concentration versus time curve at t equals 0, which we will illustrate on the next slide. Now, in the lab, actually measuring the rate of a reaction at 0 time is impossible for obvious reasons. So, in laboratory work, we often measure the average rate over the first few percent of the reaction and say that's a pretty good approximation of the initial rate. For the data we have available for the hydrolysis of t-butyl chloride, measuring the average rate over the first 50 seconds, which represents just the first about 6% of the total reaction time, would likely give us a rate close to the instantaneous rate. Now, on the next slide, we will attempt to extract both the instantaneous rate at 0 seconds and the average rate at the beginning of the reaction, 0 to 50 seconds. We will then evaluate whether or not the average rate from that 0 to 50 is a good approximation of the initial rate. So on this slide, again, we're going to compare the average rate between 0 and 50 and the instantaneous rate at 0. Here's the graph of the data, and the average rate from 0 to 50 we're going to get by finding the slope of the line that connects the data points between 0 and 50 seconds. And it's a green line. That's hard to see here, but that is a green line right there. The slope of that line is minus 0.00019. So the average rate from 0 to 50 is 0.00019 molar per second. Now, the next thing I tried here, and I did the best I could, was to draw a red line tangent to the curve at time equals 0, and then find the slope of this line by taking 2 points on the red line. And I chose those 2 points because they're easy to see. If I find the slope of that line, remember that would be the instantaneous rate at time equals 0, I get a number, well, the slope of course is negative, but I get a rate of 0.00020 molar per second. So I want you to see that the instantaneous rate at 0 is very close to the average rate over the first few percent of the reaction. So yes, we can get a good idea of what the initial rate is at time equals 0 by just taking the rate over the very first few percent of the reaction. So let's summarize what we've done so far. The rate of a chemical reaction in the absence of special circumstances decreases with time. The average rate is simply the change in concentration over a specific time period. For the hydrolysis of t-butyl chloride, the average rates were 0.000180 molar per second over the first 100 seconds, and it decreased to 0.0000560 molar per second later in the reaction. The instantaneous rate, on the other hand, is simply the rate at a specific time, not over an interval of time, but at a specific time. It is determined by drawing a line tangent to the curve at that time point and finding the slope of this tangent line. For the hydrolysis of T-butyl chloride, the instantaneous rates calculated were at 100, the instantaneous rate was 0.00017 molar per second, and at 800, the instantaneous rate was 0.000040 molar per second. Now the initial rate, remember, is technically the instantaneous rate at time equals 0. Now, since most people find it difficult to measure something in 0 seconds, and drawing a line tangent at t equals 0 of a concentration versus time curve is subject to some error, you could see how I struggled with that red line. The initial rate can be approximated by measuring the average rate over a short interval at the beginning of the reaction. Now, before leaving this lecture, let's try to see how we can handle two more issues that will come up. The first is that following the reaction rate from a different perspective, for example, we might want to follow the appearance of a product rather than the disappearance of a reactant. This is something that is sometimes convenient to do. We need to see how we might handle that and how we would report a reaction rate for reactions where the balanced equation contains coefficients other than 1. Remember, in our sample real reaction here, all the coefficients in front of the reactants and products were 1. So let's rewrite the balanced equation for the hydrolysis of T-butyl chloride and add some color coding. So we have our T-butyl chloride in blue, our T-butyl alcohol in red. And remember, this is a 1-to-1-to-1 reaction. Now the Excel plot below, the blue curve represents the disappearance of the T-butyl chloride with time, but the orange curve represents the concentration of T-butyl alcohol, one of the products, increasing with time. Again, the T-butyl chloride is disappearing with time because that's a reactant. The T-butyl alcohol, one of the products, is increasing with time. Now, since the coefficients in this equation are all 1, it makes sense that for every T-butyl chloride in blue here that disappears, 1 T-butyl alcohol will appear. So it's not crazy that these two curves are basically mirror images of each other. As the reactant T-butyl chloride disappears, the product T-butyl alcohol appears at the same rate that the T-butyl chloride is disappearing. We could do an example calculation. The average rate of disappearance of T-butyl chloride between 0 and 100, we've done that calculation before, is this rate right here. And the average rate of appearance of the T-butyl alcohol between 0 and 100, we can calculate, and it's the exact same number. Notice that when a product is appearing, which products do, that you don't need this minus sign. So this is the rate of appearance of T-butyl alcohol, and you don't need the minus sign on either side, because since the concentration of the product is increasing with time, you're automatically going to get a positive number for rate. So the rate of disappearance of the T-butyl chloride is equal to the rate of appearance of the T-butyl alcohol over the same time period, primarily because there's a coefficient of 1 in front of each of these, or more importantly, that the coefficients are equal in front of each of these. Let's write our reaction once again. We can write a general statement concerning the rate of this reaction. We could say that the rate of the reaction is equal to the rate of disappearance of the T-butyl chloride, which is equal to the rate of disappearance of water, which is equal to the rate of appearance of the T-butyl alcohol, which is equal to the rate of appearance of HCl. Now, as we showed on the previous slide, the reported rate of the reaction is the same, whether we follow the concentration decrease of T-butyl chloride with time or the concentration increase of T-butyl alcohol. And that's because their reaction coefficients are equal, and in this case, they're both 1. For the same reason, if we found a way to follow the decrease of water with time or the increase in HCl with time, we get the same reported rate because those coefficients 1 and 1 are exactly the same as the coefficients in front of the T-butyl chloride and the T-butyl alcohol. But what about measuring rates of reactions where the reaction coefficients are not all equal? Let's look at a simple example. How about this balanced equation for the formation of dinitrogen tetroxide, N2O4, from nitrogen dioxide? Let's suppose this was carried out and someone found a way to experimentally measure the rate of appearance of N2O4, and it was found to be 0.129 molar per second. Now, what would be the rate of disappearance of NO2? Well, since 2 molecules of NO2 disappear or react for every 1 molecule of N2O4 that's formed, it's probably not too hard to figure out that the rate of disappearance of NO2 would be twice the rate of appearance of N2O4, so 2 times 0.129 or 0.258 molar per second. We could write this a little differently algebraically, divide both sides by 2, so in other words, we're saying that half the rate of disappearance of NO2 is equal to the rate of appearance of N2O4. So if we were to report a rate for this reaction, since now we have 2 rates, 0.129 from the perspective of appearance of N2O4 and 0.258 from the perspective of the rate of disappearance of NO2, what rate should we report? Well, in principle, you could report either rate as long as you told the reader what you were basing it on. There is a straightforward way of reporting a value for a reaction rate that actually doesn't depend on which reactant or product you're monitoring, and this straightforward way will also allow us to compare the rates of disappearance and appearance of reactants and products, also in a straightforward way. Let's consider a kind of generic reaction. And in this generic reaction, of course, A and B are the reactants, C and D are the products, and the coefficients are in blue here and in italics. And we would say that if we wrote the rate expression this way, the rate that we come up with, this is our straightforward method, would not be dependent on which reactant or product concentration change we were following. And you'll note that we wrote this as the rate of disappearance of A equals the rate of disappearance of B equals the rate of appearance of C equals the rate of appearance of D, with the caveat, of course, as you see in front of you, that we're bringing the reaction coefficients down into fractions, where the reaction coefficients are denominators in fractions. So let's apply this to that simple reaction we saw on the previous slide of two NO2s going to N2O4. Recall we measured by experiment that the rate of appearance of N2O4 was 0.129 molar per second. We can adapt our general or generic reaction here to our reaction and write that 1/2 the rate of disappearance of NO2 is equal to 1 times the rate of appearance of N2O4. We know this by just bringing these coefficients down into these fractions. We know that the rate of appearance of N2O4 is experimentally determined to be 0.129. Since there's just a 1 here, this equality holds. And so we can say, look, the rate is 0.129 molar per second. We're going to report that as the rate, and we're going to say it's independent of what reactant or product that we're reporting. That's the rate for the reaction. How about the rate of disappearance of NO2? Again, using our formulation here, we'd say that 1/2 the rate of disappearance of NO2 is 0.129. So if we just multiply through by 2, we find the rate of disappearance of NO2 is 0.258. So what have we learned here? Well, it appears that the rate that we report should be the one associated with the disappearance or appearance of the reactant or product that has a reaction coefficient of 1. In this case, it would be the rate of appearance of N2O4 is the one we report. Now, once you settle on the proper reaction rate to report, 0.129, we can calculate the rate of disappearance or appearance of other reaction components by just adapting this general equation here. I hope at this point you're thinking that this is a lot of unnecessary algebra to figure out something that was fairly obvious. And that's a good point, but this system that I outlined here can be helpful in situations that look a little more complex. So let's look at one of those. Consider the balanced equation for the complete combustion of butane gas. You'll notice butane plus oxygen giving CO2 and water. None of the coefficients are 1, and the coefficients are all different. Suppose the rate that you could measure is the decrease in the concentration of butane over time, and you find out that that's 0.688 molar per second. So given this information, what's the rate that we should report that's not specifically based on the disappearance or appearance of any of the components of the reaction? And after we figure that out, what would be the rate of disappearance of O2, the rate of appearance of CO2, and the rate of appearance of water? Let's figure out what rate to report. Well, if we apply the general form here, we'd see that we would bring down the coefficient of 2 in front of the rate of disappearance of butane. 13 comes down here in front of the rate of disappearance of O2. And of course, on the other side of the from the other side of the reaction, we bring down the 8 and the 10. Now we know from experiment that the rate of disappearance of butane is 0.688. So we know that the rate is equal to minus 1/2 this number, 0.688. We get 0.344 molar per second. What happened to the minus sign? Remember, rates need to be positive. So based on that, what would be the rate of disappearance of O2? Well, we know that the rate from our previous calculation is 0.344 molar per second. The rate's also equal to 1 over 13 times the rate of disappearance of O2 with time. So we can solve for the rate of disappearance of O2 with time. We get 4.47 molar per second. For the rate of appearance of CO2, we know that the rate is equal to 0.344. The rate is also equal to 1/8 times the rate of appearance of CO2. We set that up as an equation, solve for the rate of appearance of CO2. We get 0.75 molar per second. Following a similar logic, we get the rate of appearance of water of 3.44 molar per second. So in summary here, the rate of disappearance of butane was experimentally measured as 0.688 molar per second. The rate that we would report would be 0.344 molar per second. The rate of disappearance of O2, CO2, and H2O can also be calculated from the general rate expression.